Hi there, this is a video about pitfalls when using MLCCs or multi-layer ceramic capacitors. Here are 4 caps that this video will look at. The 2 left ones are MLCCs, then for comparison there are 2 film capacitors on the right. Attracted by decent capacity values and prices, I was considering MLCCs to use for a repair. I have not used them much before, so I studied the datasheets, and that started a big learning curve for me. It all began with this passage in the datasheet for the leftmost axial MLCC. So these capacitors are suited for applications where dielectric losses, high insulation resistance and capacity stability are not important. Wow, that limits the use quite a bit. And then, intriguingly, Z5U exhibits a predictable change in capacitance with respect to time and voltage. Sadly, nowhere else in the datasheet is that predictable change further detailed. So I had to find out myself. Measuring capacitance while a voltage is applied is something all multimeters with capacitance test function and many less expensive LCR meters can't do. They all warn that caps need to be fully discharged before they can be measured or risk damaging the meter. Enter the TF2700, which I restored in a video recently. It has no problems in applying DC voltage biases of up to 500 volts if you're so inclined. Back in the days, this was to test electrolytic caps, which may have different capacitance whether they are biased or not. But surely I thought this will work for modern MLCCs too. The TF2700 has a socket to apply a DC bias to the capacitor under test, but the manual warns that there needs to be a series resistor to limit the current and protect the components inside the bridge, and a capacitor to provide a passage for the bridge's 1 kHz AC through the DC bias feed. Since I decided to stay below 50 volts, I choose 15 kiloohms for RL and pick the 100 microfarad 50 volt cap for CB. That is definitely an overkill in capacitance, but it turned out that with the 15 kiloohms resistor in series, applying a 15 volts bias causes the voltage to climb only gradually as the CB is charged or discharged. This is nice because it produces almost like a slow sweep over a voltage range, and you can easily see how the voltage affects capacitance. So here's my setup with a digital meter showing the bias voltage. The first candidate is the axial MLCC from KMET 0.33 microfarad at 63 volts. Because it's axial, I connected it directly to the terminals of the bridge. I'm not going too much into how to use the bridge. There is that other video for that. Just so much. If the meter is as close as possible to null, you can read out the capacitance on the dial on the right. The sensitivity knob is used to make the meter more or less sensitive. You need more sensitivity to amplify the tiny movements when the meter is close to 0, but you need lower sensitivity when the bridge is not balanced or the meter will go off scale. Lastly, in this mode, the meter deflection only goes to the right. Balancing a bridge can be time consuming. In this video I'm not going for the ultimate accuracy. Anyway, the capacitance of the axial MLCC is 0.351 microfarad. Applying the bias, and wow, I did not expect such a strong effect. That bias throws the bridge completely off. I tried first to find a new capacitance and panic a bit, but in the end I have to reduce the sensitivity to find the new balance point. The capacitance is definitely lower because the outer ring is at 0.2. 15 volts bias and the capacitance has dropped from 0.351 microfarad to 0.226 microfarad, a 36% drop. Is it reversible? Let's turn bias off and, oh yes, a massive change in capacitance again. Anyway, as the bias approaches 0, I can tune the bridge and the capacitance is back where we started. Next candidate, another MLCC, but with radial legs, so a jumper cable is needed. This is an EPCOS part, 1 microfarad 50 volts. In the interest of time I speed up the bridge tuning a bit. Well, this baby is far from spec. Instead of 1 microfarad it's only 0.689 microfarad. Almost as if this one is a 680 nanofarad cap wrongly sent out as a 1 microfarad capacitor. But I checked the value on the cap and it says 105, 10 with 5 zeros, so 1 microfarad. After the previous experience, I lower the sensitivity a bit before applying bias. Watch the needle on this bridge. This is interesting. It started deflecting and then came back briefly to 0 before deflecting again, and this time massively. Something to investigate later. Let's first see where this cap ended with 15 volts bias. It changed from 0.689 microfarad to 0.52 microfarad, an almost 25% drop. And again, a quick test to see if the change is reversible by turning off the bias voltage. And to speed things up, the answer is yes, the capacitor is back where we started. These were the only two MLCCs I had at the moment, so here's a polyester film cap of 0.33 microfarad, 63 volts, also from KMET. It reads 0.381 microfarad. Let's apply bias voltage. Nothing happened. This is full sensitivity and the capacitance had not changed one bit with 15 volts bias. And of course, still nothing turning the bias off again. Frankly, this is what I would have expected from a capacitor. And finally, another film capacitor, different build, rated 0.33 microfarad 100 volts, but I don't know the make. After tuning the bridge, it reads 0.372 microfarad. Predictably, it's also fully unimpressed by my 15 volts bias. The capacitance does not change with or without bias. Off camera, I did an exhaustive repeat of these tests for the two MLCCs with different bias values, expanding the voltage range to 40 volts. The result is this chart. The orange trace is for the axial KMET 0.33 microfarads, while the blue trace is for the 1 microfarad EPCOS part. As the earlier test already indicated, the EPCOS has a noticeable bump, in that capacitance first increases slightly and then drops, similar to the KMET. Now, both of these MLCCs are capacitors that offer the largest capacitance in the smallest form factor at a very reasonable price, and that turns out to be the issue. MLCCs are all about the dielectric material, basically the stuff that is in between the plates of the capacitor, and how stable it is against temperature and voltage variations on one hand, and its permittivity, which describes basically how much it can boost capacitance on the other. There's a 3-letter code you see a lot in ceramic capacitors which describes these materials. Here's the class 1 table, which are the most stable and generally based on calcium zirconate. C0G, or sometimes called COG, for example, has nominally a zero drift with a 30 ppm per degree Celsius tolerance. ppm standing for parts per million. Another material may be T2J, and that would have a nominal drift of minus 470 ppm per degree Celsius with 120 ppm per Celsius tolerance. The point is that while COG is very stable, its permittivity is low, so you can't get a lot of capacitance with that stuff. T2J is better, but not much. There's a reverse relationship. The more stable, the less capacitance you get. Class 2 material is based on barium titanate, which has a permittivities that are 1,000 times larger than class 1, but now you are paying with significant changes over temperature. In this class, we are no longer talking about parts per million. Here it's changes in parts per 100, better known as percent, from minimum temperature to a maximum temperature. For example, capacitance of X7R will change by plus minus 15% from minus 55 degrees Celsius to plus 125. Z5U, on the other hand, experiences a massive change from plus 22% to minus 56% over a much smaller range from just plus 10 to plus 85 degrees Celsius. While Z5U is still some variant of barium titanate, it's a class 3 material which offers even greater capacitance and even worse temperature specs. To compound the problem, barium titanate is ferroelectric material, and now there's a voltage dependency as well. Generally, the higher the capacitance and the smaller the physical size, the more voltage dependency, because the manufacturers have to make the layers thinner to fit into the envelope, which causes a higher voltage stress in the dielectric. And if there was any doubt left, oh yes, both my MLCC's capacitors use Z5U. This graph is about the temperature stability, but I think the voltage dependency of the graph would be very similar in shape. The stable materials offer only low or moderate capacitance, and materials like Z5U boost capacitance a lot, but then you get these huge slopes where the capacitance changes. One more thing to talk about is aging. All class 2 and class 3 MLCCs lose capacitance over time because when the capacitor is made, the dielectric was hot, and as it cools down, a natural polarization in the crystals occur that increases the capacitance a lot, which is of course the whole point of class 2 and 3 dielectrics. Unfortunately, over time, that polarization gradually dissipates, causing a steady loss in capacitance. I'm simplifying a lot, but that's the gist of it. The rate at which this loss occurs is specified in datasheets in % decade hours, a very strange unit. Basically, it turns out that the loss is linear if plotted in a graph where time is logarithmic. For example, an X7R capacitor with 3% decade hours loses 3% of capacitance in each time decade. In the first hour, it loses 3%, and then another 3% over the next 10 hours, another 3% in the next 100 hours, and so on. Because of the aging, manufacturers actually make their capacitors with slightly higher capacitance than their nominal or reference value. For example, 11.2 microfarads instead of 10 microfarads. As this graph shows, that capacitor will drop to 10 microfarads after 1000 hours. The time when it reaches the reference value is often shown in datasheets as well and known as the referee time, in this example 1000 hours. Of course, the capacitor will continue to lose capacitance after that, dropping below the reference value. In this example, it will lose another 3% over the next 10,000 hours and so on. Not so bad, but an X5R capacitor will age much faster, losing 5% every decade, and the referee time is just below 50 hours. A key point is that aging can be reset by heating the capacitor above 150 degrees Celsius for 30 minutes, or much quicker by soldering the capacitor onto the PCB, because soldering temperatures are much higher. Let's try to de-age my two MLCCs. First, an exact measurement of the capacitance of the axial 0.33 microfarad MLCC, which at this point in time reads only 0.3091 microfarads, about 6.4% too low. And the same for the blue 1 microfarad MLCC, which now reads only 0.6242 microfarad, about 37.6% too low. I put the caps on my heating plate, but I did not want them to touch the plate directly in case the housing melts and gets stuck. So a piece of aluminum gives a little space with a coin as weight. A glass jar over the whole thing seals it off and keeps the heat inside like an oven. Setting the heating plate to 150 degrees Celsius, starting a countdown timer when the temperature has been reached, and turning the heat off once the 30 minutes are over and letting everything cool down. The axial capacitor increased massively from 0.3091 microfarad to 0.3789 microfarad, which is now 14.8% more than the reference value. It could well be that Kmit made this cap with a slightly higher value for reasons explained earlier. The blue capacitor increased a lot too, from 0.6242 microfarad to 0.8809 microfarad, which is now only 11.9% below the reference value. Frankly, I was hoping for an even larger increase, but maybe this EPCOS cap was just made that low. Caps have usually a 20% tolerance anyway, so it would now be still low, but at least in spec. And while we're at the topic of heat, a quick test how my caps respond to heat. The first film capacitor does not care. Next is the axial MLCC cap, and as expected, there's a massive response. The other MLCC shows the same behavior as it uses the same dielectric. And finally the other film capacitor, which is again unimpressed. I was wondering if maybe the blue EPCOS MLCC needs a higher de-aging temperature. So I decided to give soldering a try, doing it deliberately slow to increase the temperature of the capacitor and the time of exposure. But that achieved only a very moderate increase from 0.8809 to 0.8846. It looks as if this capacitor is just not getting any closer to its stated 1 microfarad value. At this time, it just so happened that I needed a few 330 nanofarad SMD MLCC caps, and I decided to add them into this video. These come from eBay and the manufacturer is not stated, but I have used the seller before and so far there was no issue with the quality of their products. To use one of these in my experiments, I soldered 2 wires on. This of course has reset their aging. The cap measures 0.3518 microfarad, which is slightly above the reference of 0.33, but in line with what I would expect after de-aging. Applying the usual 15 volts bias, and there is again a small bump at the beginning, but overall the effect is far less than for the previous Z5U MLCCs. I don't even have to change the range, and with 15 volts bias the cap comes in at 0.308 microfarad, a drop of 12.4%. I took the time to do a series of measurements and added the X7R into the graph you saw before as the red trace. There is still a pronounced effect of capacity loss caused by DC bias, but it's noticeably flatter than the others. The bump at the beginning is there, but it's so small it doesn't really show on this scale. A day later I tested the temperature behavior of the X7R, which is why the capacitance value has dropped already. Interestingly, the capacitance value goes first slightly up and with more heat down, but overall the change is very small. Recalling the graph earlier, this is consistent with the green X7R trace, which increases slightly beyond room temperature and then starts dropping. After a pause of many days, I measured my test MLCC capacitors again, and their values have dropped as expected because of aging. For each MLCC, I calculated as accurately as possible the elapsed time in hours since it was last de-aged. Plotting the values after the last heat treatment and the current value on the graph with logarithmic timescale allows to estimate the aging factor for all three. It turns out the axial KEMET capacitor of 0.33 microfarad loses capacitance at about 2.5% per decade hour, while the blue EPCOS 1 microfarad cap loses capacity at 5.7% per decade hour, which is more than twice the rate of the KEMET. Both use the same dielectric material, so it seems the aging depends also on the capacitance. I'm guessing that higher capacitance needs more polarization and is therefore more affected by aging. My X7R cap aging estimate is 2.4%, but this value is somewhat uncertain. I measured the X7R properly with the LCR meter a day after I soldered the leads on. That means I missed the first decade, and this portion of the trace is simply extrapolated. Since the cap has not had enough time to fully span the 100 to 1000 hour decade, I based that aging estimate on the extrapolated 1 to 10 decade, but the value is probably in the right ballpark. There are a few other drawbacks of MLCCs. One of them, as mentioned earlier, is lower insulation resistance. I measured the resistance of each capacitor in this test, and it's certainly true that the 3 MLCCs on the right have a lower resistance than the 2 film capacitors used as controls, but it's not as dramatic as I thought it might be. Again, the EPCOS with its higher capacitance is by far the worst in insulation resistance. I should point out that these values are pretty rough numbers based on the conductance in nanosiemens, hence I do not show any decimal points. For example, the difference between the 2 film capacitors was just one least significant digit, or 0.01 nanosiemens, and converted to gigaohm, that already causes this big jump. One more thing to find out: does the DC bias dependency matter? To test this, I put this NE555 based oscillator together using a film cap at the moment. The red meter shows the supply voltage. Varying the supply voltage changes the amplitude and therefore the volume, but the frequency remains constant. I replaced the 0.33 microfarad film cap with a KEMET 0.33 microfarad axial MLCC. There's definitely a frequency change noticeable when I vary the supply voltage. It's not a surprise really. Z5U MLCCs have no place in oscillators or timers. Next, I replaced the KEMET MLCC with the EPCON 1 microfarad MLCC. Because of the higher capacitance, the frequency is of course lower. Again, there's a noticeable frequency change when varying the supply voltage. Last not least, the no-name X7R MLCC. As expected, there is a bit of a frequency change when changing the supply voltage, but definitely less pronounced as with the Z5U MLCCs. However, even if you keep the supply voltage constant, the steady capacity loss from aging basically rules out any class 2 or class 3 MLCC in this application. Well, I hope you found this rather long exploration into MLCCs useful. I, at least, certainly learned a lot about MLCCs and when to use them, or rather when not. They are certainly not a one-fits-all solution. Lots of capacitance in a small package results in large bias voltage and temperature fluctuations and faster aging. Better dielectrics means more stability but smaller capacitance and higher price. Choosing the right capacitor, MLCC or something else is not trivial and highly application specific. If you like my videos, don't forget to subscribe. There are more projects, repairs and reviews coming up. And it would be great if you decided becoming a Patreon. That would really help this channel. Thanks for watching.